All right, so we are moving through the calculus kind of for multivariable functions. The last time we just kind of did domains and ranges. That was an algebra topic. Now we're moving into limits and continuity, which was the first topic in our favorite calculus course, but now we're doing it for multivariable functions. So I'm going to give you kind of the story behind these multivariable limits here in this video, and then we're going to start evaluating a few of these things using the same strategies actually from Calc 1 and from Calc 2. All right, so story time, right? Back from the Calc 1 days. So the techniques for actually evaluating out one variable limits, a lot of them we'll actually be using. So the first thing that we learned was that to prove a limit exists, first try algebra, right? So to try to get something to cancel. So I guess this even skips one more before that, right? If you can just plug something in, that's even better, right? So maybe it doesn't divide by 0 and there's no problem. But here, kind of in any realistic problems, a lot of them, you do have to do some algebra. So if you have a problem like this with the x squared minus 1 over x minus 1, the claim is if you factor the top, then you get x minus 1s. These nicely cancel. So you get x plus 1. Again, x was going to 1, so you just plug in a 1 everywhere you have an x, and that gives you 2. So that was the first thing we kind of learned back in our Calc 1 days. Another thing that came up is that to prove a limit doesn't exist, well, you can show that the left-hand limit and the right-hand limit are not equal to each other, right? So if you choose these two different paths, right, and you see that they are not equal, then the limit does not exist. So for instance, in this case, if you were to take the limit as x goes to 2, right, well, you could break it up and you could say, well, what about the limit as x goes to 2 from the left? In that case, if you're to the left of 2, right, you're less than or equal to 2. So this is just going to be x, and this is going to go to 2, right? You have no problem plugging in a 2 everywhere you see an x. However, if you were to approach from the right, so 2 plus, right, so this denotes from the right, well, then you're bigger than 2, right? So, okay, in that case, your function's given by x plus 1. So if you go ahead and you plug in a 2, everywhere you see an x, you're going to get 3. And since these two do not equal each other, right, the left-hand limit and the right-hand limit are not equal to each other, then the claim is the two-sided limit does not exist. And then finally, our third technique, if none of these work, well, it turns out the squeeze theorem is quite powerful. And so maybe we can use the squeeze theorem to prove that a limit exists. So remember back in the days we did this sine of x over x. We proved this, that this goes to 1 using a squeeze theorem, right? Bounding it on top and on bottom and then taking the limit of those things, maybe as x goes to 0 in this case. And then finally, well, I guess no one's favorite was the epsilon delta, right? Formal definition for limits. So we use these to prove formally things like 2x plus 1 goes to 5 as x goes to 2. That is, for all epsilon, there exists a delta such that if you're within this certain range from 2, right, x is within delta from 2, then our function is within this limit 5 from epsilon. Okay, those were a huge pain. And then finally in Calc 2, we learned about L'Hopital's rule. That was really nice. Turns out, sadly, we will not be able to use that in this class. So let me kind of give you the lowdown for Calc 3, right? So these multivariable functions, how are we going to be taking their limits? So the claim is 1, 2, and 3. So that is the algebra stuff, the kind of two different paths idea showing that the left-hand limit and the right-hand limit were not equal to each other, and the squeeze theorem will be the techniques that we use for our multivariable limits. The epsilon delta formal definition is a technically correct way, right, to do these multivariable limits, though we won't be covering this in class. And I definitely recommend if you have interest in doing delta epsilon stuff, you know, for these multivariable limits, we want to recruit you to be a math major. You can take basically an entire course on this, Math 421, which is kind of a multivariable analysis course, where you really dive in to the technicalities like this. So that has an entire course dedicated to this. So if you have interest in that, we want to recruit you. You should be a math major. And then finally, number 5, L'Hopital's rule sadly does not work for multivariable limits. I wish it did. but sadly it does not. So if you try to apply it, you will often get the wrong answer, and just kind of your steps are incorrect, because again, there is no L'Hopital's rule for multivariable limits. I want to really, emphasize this, because I still see people making this mistake kind of semester after semester. So again, there is no L'Hopital's rule. Do not try this for multivariable limits. Okay, so, and the claim is there were a bunch of like really sad limit rules. Those all apply. So kind of if you take the limit of the sum, that's the sum of the limits. If you take the limit of the product, that's the product of the limits. All that sort of stuff, that applies for multivariable limits. Okay, a little bit on the notation, right? So I'm talking about that we're going to be doing multivariable limits. We want to know, how do we actually notate these things? So one notation is the limit, and you specify x and y in a point is going to, well, maybe a and b. So instead of just x going to 0 or x going to 1, or, right, you need to specify what does x and what does y both head towards. So there's the limit of our function, f of x, y, and this would be equal to some L, right, the limit. Another notation that comes up is the limit as x goes to a and y goes to b. So kind of separating this. This is the one that I often like to use here, just because it kind of separates it very nicely. For our function, f of x, y is equal to L. And then finally, one more notation. You may say f of x, y approaches L as xy, the point xy, approaches a b. And this is another kind of slick notation there for talking about limits. Okay, so I would like to go through the first and nicest technique for multivariable limits here in this video, and that's where we will end. So I wanted to prove a limit exists. First try algebra to get something to cancel. So, okay, this is kind of, we're going to be following, again, these 1, 2, and 3 from up here, right? So this is the first one kind of that we learned back in our Calc 1 days. So to try to show something, a limit exists, use a little bit of algebra, try to get something to cancel, and then you can just plug in. Okay, so that's what we're doing here for multivariable functions. So in this case, let's go ahead and see if I do the limit as x and y both go to 0. Actually, this one's even nicer than, having to do some algebra to get things to cancel. If I just plug in 0 everywhere I see an x and 0 everywhere I see a y, I would get the natural log of 1 plus 0 divided by 1 plus 0 plus 0. So this is going to be the natural log of 1 divided by 1. So the natural log of 1 is 0, and if you divide that by 1, in this case, you just get 0. So this is the nicest case scenario. You will very rarely see something like this, when it actually comes to quizzes and exams. But, I mean, if it does, great, So if you can plug something in and get a real number, do it, right? And that's the answer. However, often you get something like this. So again, I kind of switched the notation. I'm trying to get you used to all of these different notations here. So let's find the limit as x goes to 1 and y goes to 1 for this function, right? If it exists, or show that it doesn't exist. So in this case, if we were to try the same thing of just plugging in, well, in this case, 1 everywhere you see an x and 1 everywhere you see a y, you would get, well, let's see, 1 times 1 would be 1 minus 1 squared plus 1 minus 1 divided by 1 minus 1. So in this case, you would get 0 divided by 0. And we learned in Calc 2, right, these are one of these indeterminate forms, right? 0 divided by 0, it's not a real number, right? 0 divided by 1, that's a real number, because you're not dividing by 0. However, 0 divided by 0, we have issues with. Okay, so we would like to do a little bit of algebra, maybe, to try to get things to cancel. And so when I look at this up here, let's go ahead and maybe notice if you group these things even. So if I group the first ones and the second ones together and try to factor out as much as possible. This is called, of course, factoring by grouping. So if I do that, well, from the first one here, I could factor out a y, right? So if I factor out a y, I would have x left over in the first one, and I'd have minus y left over in the second one. Of course, if I distribute that, I get back to where I started. Plus, and really there's nothing in common here, so if you'd like to, you can just say factor out a 1, and then you'll have x minus y left over, right? So if you factor out a 1, you'll have x left. If you factor out a 1, you'll have negative y left. And this is all divided by x minus y. And now notice that each one of these terms, right, has an x minus y, that you have some on top and one on bottom, right? So let's go ahead and actually factor this one more time, right? Both of these terms have an x minus y. So I'm going to go ahead and factor out that x minus y on top. And when I do that, well, from the first term I'll have just y left over. And from the second term I'll have this 1 left over. And now we can very clearly see, right, this x minus y here is going to cancel with the x minus y on bottom. And so actually, right, we did a little bit of algebra and we got something to cancel out, right? And so if I want to take this limit right here, well, this would be the same as the limit as x goes to 1 and y goes to 1 of just y plus 1, right? We canceled everything out, and so we just got y plus 1. And now I have no issue plugging in 1 everywhere I see an x, there aren't any, and 1 everywhere I see a y. So in this case, I get 2. So there's my final answer. We get 2, right? And so again, this models very closely what we did back in Calc 1, right? So we factored, canceled, and then we plugged in. So that's what we're doing here. It's a little bit more challenging though, right? Because we have these multivariables, right? We have x's and y's, so maybe it's not as straightforward to factor these things. But the claim is we will use a lot of the same techniques. All right, that's where I want to end the video. We will kind of talk about these other couple techniques, right? Technique 2 and technique 3, kind of approaching at different angles and maybe using a squeeze theorem. That's going to be in class. So I'll see you guys then.